Right, we've investigated the relationship between acceleration, velocity, and displacement, and how to integrate to get relationships between them and interpret them to some extent. The natural development here then is to go from acceleration to forces. And as you'd imagine, when we're dealing with forces, we just apply F is equal to ma. So if you're given an equation for the force, if you divide that equation by m, you then get the equation for the a, and then you can go about solving the differential equation as we did in the previous section. There's a little bit extra here though, and that is there's a relationship between power and force. So the power is actually the force by the velocity. I'll derive that in the next slide. I'll show you where that's coming from, right? So the idea there is you'd replace the power with F by V. That's technically not right. And what you should be doing is writing F in terms of the power and V. So the force will be power divided by velocity. So that first point isn't right, just keep an eye out for that. Then you'd have all the forces acting on the object, because everything would be written in terms of a force and in terms of acceleration. Apply F net is equal to ma. Divide the force formula by the mass, so you get an acceleration formula, and then you can solve the differential equation with regard to acceleration and dv dt or v dv dx. Okay, so like I said, we get rid of that. So here's the derivation. It's straightforward enough. The power is work over time. And if you remember, work is force by displacement. So now we have force by displacement divided by time, and then we'll divide the time into the displacement, and displacement over time is just velocity. So what that means is whenever you're given the power, you put it over a velocity, and that will be a force that we'll use. So let's have a look at two examples with this in it. All right, we have a motorbike, mass 200 kgs, moves along a straight, level, horizontal road against a resistance of 5 or V over 2 newtons per kilogram. That's interesting. Where V meters per second is the speed of the bike. The engine exerts a constant power of 160,000 watts. Remember, that has to be in SI units. That's also kind of interesting. So the first thing we're going to do is look at the power thing. So to go from power to a force, we're going to take the 160,000 and divide it by V. And that's it. That just becomes a force then. The second thing is the resistance. So the resistance is likely due to air resistance acting on the bike. It's V over 2 newtons per kg. Now that would be V over 2 newtons if it was 1 kg for the motorbike, but it's actually 200 kg. So the total resistance will be 200 V over 2, which is 100 V newtons for that particular bike. Now just with the question 4, we drew a diagram of this. The engine exerts a power, so that's a driving force is what we're looking at. And if you look at the diagram on the right hand side, it's the 160 kilowatts, so 160,000, but we've divided by V to give us the driving force. The resistive force, then I've explained that already, it's V over 2 newtons per kg, but there's 200 kgs, so 200 V over 2 is 100 V resistive force. And then the acceleration is obviously going to the right, because we're told that the thing accelerates. So what do? We apply F net is equal to ma. We pick a positive direction, that's going to be to the right. So 160,000 V minus the resistive force, which is 100 V, is equal to the mass by the acceleration, 200a. And all you then want to do is just divide everything by 100, and you get what you're looking for in part 1, which is 2a is equal to 1,600 minus v squared over v, or 2 times dv dt is equal to 1,600 minus v squared over v. Okay, part 2. Calculate correct 3 decimal places the time it takes for the motorbike to increase its speed from 15 to 30. So we're going to integrate this. We're going to rearrange the integral. So we'll get everything with v and dv on one side, everything with t, and likely a constant on the right hand side. When we integrate it, we need to fill in our initial conditions. And what we do know is the speed increases from 15. So that means when t is equal to 0, the speed is 15. Okay, so here we go. You can use the limits of integration as well. That's rearranged. It's also a substitution method will probably be used here. So if you let 1,600 minus v squared equal to u, if you differentiate it, you get du dv is equal to minus 2v, and then you can make a substitution then with the top as well. So v dv I think works out as minus a half du, something like that. Integrate it minus a half by natural log of u will equal t over 2, sub back in for the u, and you get that second line there, minus a half natural log of 1600 minus v squared is equal to t over 2 plus c. Alright, fill in your initial conditions, 15 and 0 for v and t respectively. And then once you have your specific solution, you can then sub in a velocity of 30 and calculate the time from it. So your method will be a little bit different, but you should be able to follow that hopefully. Okay, question 2 is a vertical question. And what you need to include here is the weight of the object. So don't forget the weight of the object. Just like it was a pulley question, you'd include the weight because there's a mass. All right, so we have a particle of mass m projected vertically upwards. It's got a velocity of 100 meters per second. So when t is equal to 0, v is equal to 100. There are our initial conditions. The air resistance is that value v squared newtons per unit mass. So then if we're looking for the total air resistance, it'll be 0.0245 v squared multiplied by m, because the mass is m. And we're looking for a few things. Maximum height. So we're going to get our equations, and then for the maximum height, we know that the final velocity is 0, and we're looking for a relationship between v and x, so we're looking for x. Let's have a look at that one first. Now remember, it's projected up, and there are two things acting down. So the thing acting down with the air resistance, like I said, you have to put in the m there to give you the total resistive force. That's a typical mistake that guys make. They forget the m, and then later on they wonder why there's an m in the acceleration equation. And then the other thing you have to include is the weight. So he said it's going up, and if you don't know what direction a particle is accelerating, whatever way it's moving, you assume that's positive, and you can then assume that the acceleration is going in that direction as well. So he's assumed that acceleration is positive up, and we have two forces down. Apply F net is equal to ma. The two forces are in the opposite direction to the acceleration, so they're negative. Acceleration is positive. And then you get the equation A is equal to minus 9.8 minus 0.0245 v squared. Sometimes you'll spot that 24.5 or 245 is a multiple of 9.8 sometimes. And if you do spot that, you'll see that 9.8 is 400 times bigger than 0.0245. So you can take out a common factor if you spot it, but I'd be surprised if you do. All right, so there's our equation of motion. Now we need to find the maximum height. So we're looking for a relationship between v and x, or v and s. So vd vds equals my acceleration formula. Rearrange it, integrate it. It's the same idea as the previous question, that we needed a substitution for the bottom term, and then the derivative of the substitution would allow me to cancel the v dv on top. And look, you work through it just like before, and you get a height of 66.5. Let's have a look at the second part, the time taken to reach the maximum height. So in that case, we're looking for a relationship between x and t. Now, what I would be looking at here is, rather than doing that, we're looking for a we're looking for time, right? So what you can do here is say, I'm going to pick out my acceleration formula. I know that at the maximum height the velocity stops. I'm looking for the time when that occurs. So that's a relationship between v and t. So leave a equal to dv dt, rearrange it, integrate, so on, and you get t is equal to 2.803. What I was going to say was, I could have used, or would have used, the velocity formula that I got after integration. So I made v the subject of, let's see, so the third line down, a half ln 400 plus v squared equals that thing plus c. I would have got what c was, and then I would have made v the subject of the equation. So v is equal to a whole host of other things, and then I would have let v equal to dx dt. Got a relationship between x and t, and then the x value would be the distance it travels to reach the maximum height, which is given in the last line. And that's an alternate way of doing part 2. You probably won't do that, to be honest, but there you go. Okay, 3. The average speed of the particle from its launch until it reaches its maximum height. Average speed is always total distance over total time. So it's part 1 divided by part 2. There we go, 23.7. Final part 4. Find the speed of the particle as it passes through its point of projection on the way down. Alright, so what we know is at the maximum height, it's got a particular velocity which is 0. So what I'm going to do is I'm going to draw the diagram when it's at its maximum height, put in the initial conditions, which would be when t is 0, v is 0, and then what we want to do is find the speed of the particle after it's travelled, was it 66.5 meters, or however far it travelled to get to the maximum height. And what we see is the problem, or the difference between this and what we did with 1 and 2, is air resistance is the opposite way around. So the weight is still down, but because the particle is accelerating down, air resistance is up. It then changes your acceleration formula. We're looking for a relationship between v and x, integrate it. So that brings us down to the integral from v to 0 of v over 400 minus v squared dv equals the integral from 0 to 66.5 of 0.0245 ds. I would have integrated that and put in my initial conditions, and you'll get out a constant value. And then we're looking for the velocity after the thing travels to 66.5, which was the distance from the initial point of projection to the maximum height. Fill that in, and it works out as 19.6. And you can compare there to see the difference in the velocity on the way up and the way down from that initial point of projection. It had to be projected at 100 meters per second to reach a maximum height of 66.5. And then when it fell down, the velocity when it reached the height of projection was only 19.6. And that's due to the air resistance being in the opposite direction to the weight as the particle falls down.